But is your grid spacing in Z changing constantly, or is it just like more or less constant for the lower half, and then you make the spacing wider and wider? Because up there the stuff is transparent, and then you wouldn't bother much about getting radiative times to correct there.
Oh, but you can actually, of course, also use horizontal rays. Strictly horizontal rays.
Or can?
You can, of course, because it's only non-equidistant Z, right?
Yeah, it's not warm, right?
Yeah, and it's still rectangular.
You mean I can have, in non-equidistant grid, I can have vertical
and horizontal, just not slanted rays. That's going to be difficult, I think. But as long as you raise along coordinate axis, won't be a problem.
But you really only need this when you want to do convection, really, at the same time. Is that right?
Right. I really want to path for convection since now I have these MDI in my hologram, and I have these not suitable convective motion, and I hope if I can have something like a convection that I can add a flux tube, this is a convection around here.
Yes.
And this flux tube will suppress this convection, which should be so hard to implement.
So what was the time scale for the simulation? They are very short, right? Time step is
short. It's in physical values. It's I have 1 microsecond per time step, and I need to have 2 hours solar time to be calculated. So yeah, so clusters running all day and takes half a year to simulation to end. Yeah, it's crazy.
So what, you calculate for 2 solar hours? That's quite long, right? So that means 3 million times that.
Yes.
No, billion.
More. Yeah.
Billion. 3 billion times that.
That was 1 to 10 to minus 6. Sorry. 10 to minus 6.
Yes, that's what it said, yeah.
Okay, so it was it again.
So
no, so this is a pencil time step, sorry, and it's 1 millisecond. No, sorry, 1 millisecond.
yeah, so it's 3 million.
Otherwise it would take 1,000 years. I calculated it takes, our new cluster was so fast on the slide he shows yesterday, or today, it will take 50 days for 2 hours on our cluster. But I don't know if it takes much longer than it takes the radio transfer. So, do you think it's factor 2, 4, 10? No, 2. Factor 2 more?
Most.
As much as 50 days or 100 days. How many processors? We do have 70 or something about 80 processors. We have 2 simulations running each 32 processors.
But how deep do you think the convection zone, or how shallow can you make it in order to be still physical? You don't want to make it too deep, of course.
Yeah, it should be just 1 turnaround, obviously.
Yeah.
It would be sufficient to have a more proper.
I mean, it could even be, of course, this turbulent driving that Drew and I really looking at. I mean, we are basically interested in letting the magnetic field out of the turbulence. We're not doing convection, we are driving the turbulence. And I think we could just also do the same thing. There would be helical driving of the turbulence, and the magnetic field has to go out in order for the dynamo to work. And it would produce these loops, hopefully, that you are having implemented anyway.
So with no flux in the lower bundle. So what is the boundary condition for these? What do you say?
We don't know.
The boundary condition for what?
For the magnetic field, or for the electric
Where?
on the bottom. Or
On the bottom of the box, you mean?
yeah.
That is a perfect conductor. The magnetic field is generated itself and is in the box. There's nothing involved, of course. And false dynamos are much easier to handle, obviously, than convective dynamos. And maybe they are actually also more physical in some sense. Simply because the motions are of a certain size, whereas in the convection case they are probably bigger than they would be in reality. It's a big one. Thanks.
And in this case, it would give me the advantage to add again an observation, to add a real field configuration, just to analyze. The goal is to compare with observations. A complete standalone good MHD simulation I can't really good compare. So it would be nice to have a field configuration with.
Okay. Yeah, there's by the way an interesting concept that is called data assimilation. That's a method. That's in the name. It doesn't really explain anything unless you know this term already. If you look for data assimilation under Google, you will find the right explanation what that means. So basically what this means is that you do like weather prediction. If you run, of course, a weather model, does anybody know what meteorology is? I mean, if somebody runs a weather simulation, that's not that, I mean, of course, they have 1,000 million mesh points, and then you ask, so what's the weather like today on all these million mesh points? And then they say, okay, we can't measure anything here in this high atmosphere so quickly, and you measured something 2 days ago, but that's probably of no use now. So the problem with weather prediction is you have lots of information, but not really such that you can just put it as an initial condition, and then put it into your regular mesh, and then start, and run for the next 15 minutes or 24 hours. So instead what you have is you have actually a simulation that started, for example, in the year 1970. And then they synchronized this using certain mathematical techniques. They synchronize this to the actual weather at the minute. And that's called data assimilation. So there's a complicated theory in this which tells you exactly by how much can you put forcing terms into the actual equations such that you will actually approach the weather as of now. So that means you run your simulation at the same time as you get new data in, anywhere in the point. And whatever you get, you put this as useful information, and it will keep your simulation as synchronous as it can possibly be. So I think that's the same thing that you have to do here. And then it really doesn't matter too much whether you do forced convection or forced turbulence or convection.
So using forced convection and then add forcing term.
I mean, it's not really a forcing term. It's I just call it a forcing term. But it probably actually corresponds to a forcing term. So there's textbooks, big textbooks about this. And Petri knows about this, and at least has heard lectures about this. So did I. Maybe that's something I can check back to in the connection. And you certainly cannot just take anything and start, and of course it will diverge from the real sun as quickly as it can be. So you have to keep it in sync. It's really like weather prediction.
Yeah, that's
the same thing. Right? What else do we have? Yeah. I think it's very good, the simulation. It looks almost like the real trace images, of course.
Yeah,
and I think the major difference is that the trace images are really showing a lot of swirl, which you don't really have in your simulations. That's velicity, of course, that you really see in these trace images.
Yeah, but there's different distributions too. I have a periodic boundary with X and Y, and so I have my setup looks like several active regions connected to each other and stuff like this. The other big point is that the trace loops are much thinner than the one I have here.
Oh yes, yes.
But
well, there wasn't another. It was another issue, of course, that the Buddhist simulations were also really criticized. That in your case, I think the talks seem to expand as you go upwards.
It's less than. If you look at this one, this doesn't. It doesn't depend on that.
Is that because of your field line diffusion, or okay?
I don't know. But this works much better than by Buddhism. It's not expanding as this.
Interesting. Yeah.
There's one here in the picture is this looks like expanded, but these are two loops which are behind each other.
Yes.
There is no, they are not expanding as in good simulations.
That's very good. Okay. Good. So, thank you again.